So my name is Johan Hovold. I work as a consultant doing kernel development primarily for embedded systems. I am the maintainer of the kernel's USB serial system, which is why I take an interest in the topic of this talk. I also maintain Greybus together with Greg Hartman and the new GNSS subsystem. Greybus, for those who haven't heard about it, is an application layer in the OSI model sense of the word for the Juniper interconnect. Came out of Google's Project Ara, the attempt to build a modular mobile phone. Today I'll give an introduction to the still fairly new serial device bus, which aims at making serial attached devices fit better into the Linux device model. The UARTs and RS-232 has been around for a long time now, at least since around the 1960s, probably a few years before that. And it's still a common interface for things like Bluetooth, NFC, radio, and GPS devices. And while the kernel provides an abstraction for the serial connection itself, a serial attached device is more than just the I/O interface. You typically have other resources like GPIOs and interrupts that you need to be able to manage. And so far, there hasn't really been a good way to model such associated resources, something which is, of course, important, at least for power management purposes. And unless you wanted to write your driver entirely in Userspace, the kernel support has so far been limited to so-called line discipline drivers, within quotes, because they're not really drivers in the kernel's driver model sense. And these have the drawback that they have to be configured and initialized by Userspace. So, brief outline of the talk. I'll start with saying a few words about the TTY layer before discussing these two options that were previously available, namely to write your driver in Userspace or to write one of these line discipline drivers. I'll then go into how serial was implemented, how it hooks into the TTY layer, before presenting the driver interface that you need to use if you're going to implement your own serial driver. I'll finish off with discussing some limitations with the current implementation and list some items for future work. So the TTY layer then, as I mentioned in the beginning, ultimately provides this abstraction for the underlying serial port hardware. The character device that you've all been using, the dev TTY-S ones, for example, is what a Userspace application would use to communicate with the underlying hardware. Beneath the character device, we have the line disciplines, which is where the I/O processing in the kernel is currently implemented. This is where, for example, the line editing facilities, the canonical input mode, is implemented. It deals with echoing, emitting errors and various error conditions, and emitting signals in various input conditions. Beneath the line discipline, we have the TTY ports, which is where the input buffering is implemented. And this is a kind of abstraction layer for dealing with the POSIX semantics involved. When opening a port, you need to raise the modem control signals, DTR, RTS, and so on. Beneath the TTY layer, we have the actual TTY drivers, which knows how to speak to this particular hardware in question. And in this image, I've divided it up in a core part TTY driver and a lower level driver, because this is often how it looks like in the kernel. We have the serial core with all its various serial drivers, and USB serial uses a similar division. The TTY drivers define a set of TTY operations with the upper layers call into. So previously, you could go about writing your driver in Userspace, which means you would typically use the default line discipline, the TTY. You would then have to tell your application in Userspace, your driver would need to know which port to open and what line speed to use. And while some associated resources like GPIOs and interrupts are available to Userspace through GPIO-lib sysfs interface or the new character device interface, other resources like regulators and clocks don't have Userspace representation. You also wouldn't be able to use the kernel's frameworks for power management. You would need to deal with things like making sure you get notified when Userspace initiates system-wide suspend. There's also an issue then with defining wake-up interrupts. There is no way to currently do that through GPIO-lib, even though there are ways around that by exposing those GPIOs as GPIO keys, for example. Also, you need to implement your own firmware management. You cannot use the kernel's infrastructure for that either. But sometimes and particularly when you need to interact with other subsystems, you need to have your driver live in the kernel. For example, if you need to pass on data to the Bluetooth stack, input subsystem, and so on. And this is where the line discipline drivers come in. So you would then need to have an application open, serial port, switch the line discipline, and then the line discipline would register further class devices, which would be what Userspace would be using to communicate with the underlying hardware. These class devices would then remain registered while the port is open. So this means that we need to have these entities in Userspace, these Userspace daemons, to initialize the port, switch the line discipline, and we have a few examples of common daemons that do just that. The LE-attach, input-attach, AGI-attach, which has been renamed Bluetooth-attach. And for line discipline drivers, the kernel's firmware infrastructure is available, but there are still issues dealing with other resources like GPIOs and clocks. I'll get back to that in a minute. First, we'll take a look at this example. Bluetooth, and this is essentially what the AGI-attach or BT-attach daemon does. You need to open the port, so you need to know which port to open. You need to configure the line settings, and you use your NIO control to switch to the Bluetooth and AGI line discipline. And in the Bluetooth case, you also need to specify which UART protocol to use. So it's only when this second NIO control returns that you would get access to your Bluetooth device. So graphically, we have something like this. When the system boots, the kernel goes out, parses your device tree, registers your platform drivers. They get bound to their respective drivers, which registers with the TTY layer. And so when the system is booted, you have your TTY01, for example, character device. You would then need to run your HA-attach daemon, which opens the port, switches the line discipline to the Bluetooth line discipline, and only then can you access the class device, HI0, for example, to bring up the Bluetooth interface and do anything interesting with it. So the problem with these line discipline drivers is that the description of what is connected where and how still needs to live in Userspace rather than being coded in firmware, such as device tree or ACPI. So we need these Userspace daemons to know which port to open and so on, and we don't get any kind of automatic discovery as we would if we had device tree and ACPI description of these things. Furthermore, since we don't have a description in firmware, there is no good way of describing and looking up these associated resources like GPIOs, pin control, regulators, and clocks. And these are obviously things that are useful and needed for proper power management. On the power management note there, the fact that the port needs to remain open is also something that impacts the power consumption, because an open serial port would typically prevent the underlying serial control from going into runtime suspend. And for line discipline drivers, the firmware loading, firmware framework of the kernel is available, but loading firmware onto a device typically involves targeting something like a reset GPIO, and since we don't have access to those, it's still not an optimal solution. So this are some of the motivations behind Serial Device Bus, or SERDEV as it's known for short. It was implemented by Rob Haring of Linaro, and it's a generic bus for UART-attached devices. And the immediate aim was to replace some of the Bluetooth line disciplines, and particularly this HEI-attached and BT-attached daemon. But it's based on some earlier work, earlier efforts, particularly involving dealing with power management of a particular GPS device that was found in one of the OpenMoko derivative phones. The bus itself was merged in 4.11, but due to some initial issues with the way it hooked into the TTY layer, it was reverted and then enabled for serial core only in 4.12. So SERDEV introduces a new bus type. It's named Serial, not SERDEV, and the concepts of SERDEV controllers and SERDEV devices. And since devices is such an overloaded term, these are sometimes also referred to as clients and slaves. And I will be going back and forth between these three, so watch out for that. There is only one implementation of the TTY of a SERDEV controller in the kernel, and it's a TTY port controller. And that means that it's sometimes incorrectly identified with SERDEV, but we could have other implementations. And this TTY port controller works by having the TTY driver register a controller and a client whenever there's a client defined in firmware. And when that happens, then the controller replaces the TTY character device. You don't get any TTY 01 S1. And the clients, as I mentioned, are described by firmware. The initial implementation supported device tree, and since 4.15 we support ACPI as well. So if we return to the Bluetooth example, we now have something like this instead. The system boots, register TTY drivers, devices and drivers bound, and when the TTY driver registers its port with the TTY layer, we now call into SERDEV core, which go out and checks if we have a description in firmware. And in this case, we say that we do. So instead of registering the character device, we register a SERDEV controller and a client. Once the client is bound to its driver, it would then go about and register the class device, the Bluetooth AGI 0, so that when the system is booted, you immediately have access to your Bluetooth device and you can run AGI config immediately. And this we can compare to the old situation where we've now done away with AGI attached completely. We are bypassing and not using the line discipline at all. And the most important thing here is that the SERDEV client now has a firmware representation so we can model these associated resources. And also the port doesn't need to be open at all times, something which hurts power consumption. So just a few words about how this particular TTY port controller has been implemented and how it hooks into the TTY layer. I mentioned that the TTY drivers are registering controllers and slaves instead of TTY devices, class devices, whenever there's a client defined, and that's done by registering their ports using this new helper function, TTY port register device SERDEV, which takes care of going out and looking in firmware and so on. The TTY ports themselves have gained two new fields. It's a pair of TTY port client operations, callbacks for incoming data, and write wake up notifications when there is more room in the outgoing buffer. And in normal case, these client operations would simply be forwarding data forwarded to the line discipline, but now they're forwarded to the SERDEV driver instead. And in the other direction, if for changing things like baud rates and so on, the controller interface is implemented using the TTY layers helpers and those TTY driver operations I briefly mentioned earlier. Okay, so if you want to use this is perhaps more interesting. It's an example of how the device tree bindings would look like. So a device tree binding for a SERDEV device is simply defined as a child node of a serial port node. And there are currently 3 generic properties defined, of which only the compatible property is required. Max speed and current speed are supposed to be used in those cases where the driver itself needs to, for example, lower the maximum speed that the driver can use in a particular implementation because of some hardware limitations. And current speed, likewise, if the bootloader, for example, has changed the default speed of the device. Now that you have one of these firmware descriptions, we have a place where we can describe our additional resources. So in this example, we have a Bluetooth node, which is a child of the first UART. It has a compatible property, and it specifies now an enable GPI on a clock. And this could show up like something like this in SysFS, which is a reflection of the kernel's internal device tree. Here we have 2 UARTs. Both are being managed by the OMAP UART driver. The first one doesn't have a device SERDEV slave or device described by firmware, so there we get the normal TTY 01, 00 class device. Whereas in the second case, the class device has now been replaced by a, this one doesn't work, controller, serial 0, and a SERDEV client, serial 0-0. And the client here we can see is being managed by the AGI TI driver. It's on the new bus, the serial bus, and it has registered the class device HEI0. All right, so if you want to write your own seriative driver, the interface that you need to use resembles that of the line discipline operations, which is fairly natural since we're, in a way, replacing the line disciplines here. So you have functions for opening and closing a port, changing the terminal settings, writing data to the device, modifying or reading back the modem control signals, and a couple of callbacks for incoming data and for getting notified when there's more room in the outgoing buffer. And there are a few additional helpers that are implemented based on these primitives. This is in fact the full set currently. They all take a pointer to a struct seriative device. We have functions for opening, closing a port, changing the baud rate, enabling hardware flow control, changing the parity settings, writing a buffer, waiting until the outgoing buffer has been drained, flushing the outgoing buffer, checking how much room there is in it, and modifying and retrieving the modem control signals. One thing to note here is that seriative doesn't enforce any write serialization. This shouldn't be a problem. TTY drivers are supposed to be able to handle concurrent calls to call, calls to write. But since the TTY layer generally serializes things, this may not have been tested fully, so you could expose some hidden bugs. There's also no operation ordering enforced by core, seriative core. So you could, for example, try to change the baud rate of a seriative device which you haven't opened yet, and you would crash, hit a null pointer to reference probably. All of these functions except write buff and write during main sleep. And in the other direction, I've mentioned the callbacks already. We have two callbacks for incoming data and for write wake up notifications. Receive buff is called in work queue context, so you can sleep, and you should return the number of bytes that your driver has accepted and processed. Whereas the write wake up callback is typically called in interrupt context, so you cannot sleep. All right, so if we put all this together, here's an example of what a seriative device driver might look like. We have a struct seriative device driver you need to fill out. It has an embedded device driver struct where you set your name, your device tree match table, your ACPI match table, and your power management operations. Other than that, it's just a probe and remove callback, and we have a convenience macro for registering these slave device drivers. In your driver's probe function, what you do, besides the normal allocating your private data and setting things up, is that now since this seriative device that you get passed in has a firmware representation, you can use things like clock get or other helpers to retrieve these resources like clocks, GPIOs, and so on. You would then typically store your seriative device in your private data so you can access it in your class device, your class callbacks, and you would set your private data as driver data for power management operations, SysFS attributes, and so on. The important thing here is that you need to set your client operations before opening the port, because that defines the callbacks for incoming data, for example. And if it makes sense for your particular application, then opening the port at probe time may be warranted, but it's often best to defer that until the actual device gets used, for example, when you bring up the Bluetooth device. So a new feature now in 4.19, I mentioned before, you can set your power management operations, and you can use runtime power management for your client devices. That has been possible since the start. And that means, and the idea here is that you can power manage your client devices independent of the serial controller. So you would typically, like we do for I2C, you can have your client device be active, but you only power up the controller whenever you need to do I/O. And this is typically how serial controllers are implemented in the kernel today, but we have a few examples of device drivers that implement more aggressive forms of runtime power management, which allow the controller to go into runtime suspend while the port is open. And this new implementation for controller runtime PM that was added in 4.19 allows seriative device drivers to be able to utilize this fact. And this works by having the seriative core take a runtime PM reference at open, but an aware seriative driver can put that reference and again allow the device to go into suspend. And this may be all that needs to be done. For example, if you have a protocol where you only send data, you only need to send data, then the serial controller will automatically resume when you're sending data. When the outgoing buffer has been drained, it will go into suspend again. But the problem has to do with incoming data. If the controller wakes up on incoming data, that often means that you lose the first few bytes, and that may not be acceptable. So with this implementation, the seriative device driver can resume the controller by acquiring a runtime PM reference ahead of time when it expects to input, for example, based on some kind of out-of-band signaling or the protocol itself if it's request response. As I mentioned, only a few drivers support this today. In particular, it's the OMAP serial driver and some USB serial drivers. But there are issues with the OMAP implementation. It's not really the aggressive runtime PM that's broken, but rather the fact if you don't do it, then your controller will go into runtime suspend when you close the port. And there are some discussions that needs to happen here about having a generic interface for managing this feature of turning on and off this kind of aggressive runtime PM. So, as I promised, I'll discuss some limitation with seriative, and one of the obvious ones that stands out is that it's for serial core only. As I mentioned in the beginning, it has to do with some lifetime issues that are still a problem, some legacy TTY drivers that need to be updated. But most importantly, it's because seriative doesn't have any hot plug support. This wasn't a use case that was considered, and it was something that was left to be decided later. And I'll get back to that in a minute. It's single slave only. There's no support for any kind of generic muxing or for dealing with multi-drop buses, RS-485 and so on. And while you can now configure the controller to use hardware flow control, this only applies in the outgoing direction because there is no pushback mechanism implemented for input flow control. So if your client driver can't keep up, there's no way of informing the lower layers, and data will simply be dropped. But that's probably what you want to do anyway. There's plenty of buffers in the TTY layer, and if you can't keep up with that, you have bigger problems. And since we've done away with the line discipline, which is where input processing takes place, we no longer have access to things like software flow control. We don't get parity framing or overrun errors propagated up. And you don't have access to break signaling. So serial port hot plugging is generally implemented using TTY hang-up callbacks and file operations, so that when a port has been hung up, we replace the default file operations with the hung-up operations, which only return an error. But the problem here is that seriative doesn't use the file abstraction at all. So this will require some changes to the TTY layer. And as I mentioned, this is part of the reason for the initial revert. We can't have something like this enabled for USB serial, for example, before this has been solved. We still have PCI hot plugging. You could theoretically hit this if you try to jank out your PCI card. A related issue to hot plugging is how do you describe what's connected on the other side of those buses? If I plug in a USB serial connector in my laptop, this is my laptop, but still, I don't use Mac. How do you describe what's on the other side? And one way of doing that could be to utilize device tree overlays. Problem here is only USB has some support for device tree overlays. We also had a problem with if we have dynamic topologies. Oh, I should mention that USB serial has support for device tree, but it's mostly useful for things like static topologies. If you have an Ethernet card that's soldered onto the board, for example, so you know which port the Ethernet device is, so you can set your MAC address or whatever for it. But if you plug in hubs and then in the end you plug in a USB serial device, you have no way of describing there is no complete device tree leading up to the USB serial device currently. There's also currently no in-kernel interface for getting these interfaces into the kernel, and it seems it's still a pretty long time before if we'll ever get that. Some devices are self-describing in the sense that they don't need that kind of input from Userspace. So we have, for example, an example of a pulsate HDMI CEC USB device, which presents itself as an ACM generic serial port, and it can be used to control your TV over HDMI. And this could be a device where we should be able to just simply pass something equivalent of a compatible string from the TTY driver into SeriDev core in order to have this particular class device show up immediately when you plug the device in. Instead of what you need to do now is to start LD-attach and switch to a particular SerIO protocol driver. Some minor issues, more aptly named labeled quirks. I said we've done away with the line discipline, but the line discipline is in fact still allocated, and it is also called into. It's a problem with this kind of retrofitting of something like SeriDev into the TTY layer, which is complex enough to begin with, so we end up with artifacts like this. The SeriDev controller is always allocated, even though you don't have a SeriDev device defining firmware. So you would allocate and register the controller, and if we don't find any firmware representation, we unroll and we deregister and deallocate, which is inefficient at best. I already mentioned that you won't get the character device if you are using SeriDev. And this is more of a feature than a bug, but some people have both been surprised by this fact, and there is some discussion about if it would at all be possible to have both the TTY device and using SeriDev and be able to switch between the two. I already mentioned that there's no operation ordering that you need to watch out for. And we do have a potential problem with code duplication and backwards compatibility, as some of these older line discipline drivers are now being converted over to SeriDev. We can't simply remove the line discipline drivers. We need to continue supporting them for backwards compatibility reasons. And this has already led to some of the Bluetooth implementation being in practice copied and now needs to be maintained in 2 copies. I already discussed the naming inconsistencies. The bus is named serial, and we use SeriDev device client and slave interchangeably. Another thing that's bitten people is the Kconfig for SeriDev. There are 2 symbols to enable SeriDev. One is for the bus and the core itself, and one is for this particular TTY port controller. So the first symbol, serial dev bus, is what your driver should be depending on, because that's the build time dependency, whereas the runtime dependency is that you need to have an actual TTY port controller implementation as well, and that's serial dev control TTY port. The problem here is that the bus itself can be built as a module, whereas the TTY port controller is Boolean, and that's the fact that because of the fact that it depends on the TTY layer, which is compiling only. So if you choose SeriDev bus to be modular, you won't even get a chance to select the TTY port controller, and you won't be able to use SeriDev. So watch out for that. So far, we have about 10 drivers merged, 6 Bluetooth drivers, a Ethernet over UART driver, and the new GNSS subsystem I mentioned briefly in the beginning there, with 2 drivers for surfstar-based GNSS receivers and U-Blocks-based receivers. And we have an MFD device for a kind of supervisory processor implementing watchdog backlight features over a serial connection. I want to say something really quick about the Broadcom driver. It's a Bluetooth driver, which is a sort of precursor to SeriDev, and it had hacks for additional resources and power management. And it worked by having the ACPI or platform code register a platform companion device, which is a child of the serial device. And this device would then have descriptions for GPIOs and clocks. And when a platform device is registered, it would list it in, added to a global driver global list. And later, when the line discipline has been opened and you get your callbacks from the Bluetooth stack, you would go in and look in this this list and see, do we have the same parent serial port? And if so, the line discipline would call into its sibling device in order to be able to manipulate the GPIOs and clocks. And this is just an example of the kind of hacks that you needed to resort to before SeriDev. This driver gained ACPI, and SeriDev itself gained ACPI support in 4.15. But we still have a risk of running into regressions here because of the fact that you can still use the line discipline drivers. If SeriDev isn't enabled, you can still access the device using the line discipline, but now your power management is broken. And we have similar hacks in the HI Intel driver, and that hasn't been converted to ACPI and SeriDev, so this is broken now. Just say a few words of what's brewing on the mailing list. We had the first NFC driver posted last week. I think there was a V4 posted 2 days ago, which adds support for the UART interface for this particular NFC device to an existing driver, which already supports I2C as well. There was a proposal for a LoRa socket API that was posted in July. It's a kind of long-range, low-powerless wireless technology, and those controllers are managed over ASPI or UART, and so far they had to be handled in Userspace, but now we can move things into the kernel. Related to hot plugging, the way to describe what's on the other side of a USB serial device, for example, there's been some discussion about that back in June. A patch series was posted, but it's more of an RFC really because there are some issues with this. But it shows this question keeps coming up, so we're going to have to look into that pretty soon. And a part of that discussion, I also posted some patches that I've been using for testing SeriDev with USB serial. So I added device tree support and SeriDev support to USB serial. But as I mentioned, I won't be merging these until we have proper hot plug support in SeriDev. But you can still use it for static topologies and for testing. So I'm going a bit fast now, so I'm running out of time. Sorry about that. The thing I wanted to discuss and mention here today when I had the ACPI maintainer in the room, I have mentioned it before, I think, but we have another issue with the ACPI support that was added in 4.15, besides the one I already mentioned. And it is the fact that if you have ACPI tables describing that you have, for example, a Zigbee or a GPS device connected to a serial port in your system, SeriDev will now claim that port, so you won't get a TTY character device. And this was reported back in April, and it still hasn't been fixed. We probably need to add some kind of white or blacklisting, depending on which ACPI IDs, what kind of devices that we support. At least until we have implemented drivers for all those devices out there, which are currently handling Userspace. As I mentioned, this still hasn't been fixed. That there was another bug fix, a bug report coming in only last week of someone hitting this on a different system, as now people start updating to 4.15. So this is a regression. It really should be prioritized, yeah. This is just an example of things that's been posted before. We had a backlight driver could be run through SeriDev. There was some proposal for adding MUX support to SeriDev, which could be used to implement generic support for things like RS-485. And there was an I2C controller driver there as well. So finally, items for future work, obviously address the quirks and limitations that I've highlighted, and not least adding hot plug support so we can enable this for more TTY drivers, including USB serial. Possibly look into if we can add some generic multiple slave support. There are Bluetooth drivers that still needs to be converted, and other line discipline drivers include NFC, CAN, and some other CRIO drivers. And here's just, if you want to find out more about SeriDev, I can recommend looking at the code. It's a bit involved because of the intricacies with the TTY layer, but it's only these 3 files. It's really not that much code. We have device tree bindings, and this is an article outlining some of the prehistory of SeriDev, how we ended up where we are today. So that was it. Thank you.
Thank you. Questions? Okay.
Okay, firstly, to check what I understand you correctly, if I have some UART device, I need to implement several callbacks in this device to use this serial dev API, yeah?
Yeah, you need to implement a serial driver. Yes.
Why do I need to implement this serial dev callbacks? Why isn't it possible to implement this serial dev using only TTY callbacks? Because it have all the control of TTY device.
Yeah, but we're not using the TTY character device implementation anymore. That's something that's exposed to Userspace. But now we're trying to use the serial port from within the kernel, so we need to hook into the TTY layer at a lower level.
Yeah, my question was, isn't it possible to change TTY layer don't change every UART driver in kernel?
Oh, you don't have to change the UART drivers. The UART drivers are the same. So the TTY drivers themselves that you use to actually talk to control the serial controller, they remain unchanged. So they would be used regardless of whether you are using a serial driver and accessing the port from within the kernel, or if you're exposing it to Userspace and you have Userspace accessing the port. So the serial device drivers is a new entity that's separate from the serial drivers. It's similar terminology, but serial drivers are independent from the serial drivers.
Oh, okay.
Thank you. Okay, I see.
Okay, thank you for presentation. Could you a little bit maybe elaborate about the difference between about relation of the serial and TTY drivers? So is TTY drivers actually completely orthogonal to this USB serial, or actually to this serial devices, or actually they use code of each other, and which one is actually supposed to use which code?
Yeah, so if we take this example here, well, here we have both situations actually. So the old situation on the right and the new one on the left. You see the TTY driver part is the same in both instances. So this is the driver that knows how to speak to, for example, the OMAP serial controller. And the difference is only in the upper layers. We've done away with the line discipline and the character device, and instead we now have a consumer within the kernel, and the serial client here is the device where your serial drivers would be binding to. So your serial driver would be controlling the serial client entity and speaking downwards, so to speak, to access the hardware.
Okay.
Thank you. Are there any other questions? Okay, let's see.
Hello, thank you for the talk. Are there any differences in interaction with this new SerDev lib from Userspace?
So the idea is that Userspace, things should be simplified for Userspace. So you don't need to do any setup or anything like that before you can access your Bluetooth device. So immediately when you have a system which is properly configured, where you have your Bluetooth device described by firmware, immediately when the system is booted, you can just access your HEI 0 device. So that's the change for Userspace. Userspace no longer has to deal with serial ports at all.
And will be there any Userspace library to target the SerDev lib specifically?
No, since it doesn't provide any Userspace interface, it's all going to be dependent on what kind of subsystem is using these serial drivers, if it's Bluetooth or if it's NFC or if it's something else.
Okay, thank you. Probably we have a minute left for the last question. 1 second.
Do you send any UDEF events when the new device appears?
Yeah, you will get UDEF events as with all devices that get added to the driver core device tree would be sending out device tree when you're registering the controller and the slave device.
So in the new scenario, we're getting only one event, right? And in the former scenario, we were getting two events.
So in the former case, you got an event when the character device or class device, the TTY device, was registered, and then later when the network device became available. And in the new case, you actually get three events. You get an event when the SERDEV controller is registered, you get an event when the SERDEV client is registered, and when the SERDEV client driver ultimately registers the class device, you get a third U event. So they all have representations in the device tree.
How Userspace can use the event from SERDEV client?
You can't. It's not really useful.
So
it's just something that's sent by driver core.
All right.
Yeah.
Thank you.
Thank you. So Johan, what is the best question you received? We need this.
I already
Single
forgot
one.
the questions. I really.
Yeah, you can.
So who was? First question gets the prize because he spoke first.
Okay. Thank you very much.
Thanks.
And